So, hi everyone. My name is Shizhe. I'm a research scientist at INRIA Paris, the Willow team. And I'm very glad to be here to present our recent works on robotics titled 3D-Enhanced Robot Foundation Models. So first, I would like to briefly introduce our team, the Willow team at INRIA Paris. So our research focuses on computer vision, machine learning, and more recently on robotics. We have a variety of robots in our lab, including the mobile robots Tiago, the biped, and quadrupeds. On the manipulation side, we have the robot arms equipped with parallel grippers as well as the multi-finger hands. And more recently, we got the humanoid robots to perform more challenging tasks. And well, my long-term research goal is to create the general-purpose robots that can be instructed to perform any different real-world tasks with human-level skills. For example, we could simply ask the robot, can you throw away the Coke can and clean the table? And then the robot should be able to understand this instruction, perceive the 3D environments, and plan the next steps, and finally execute the actions accurately. So this is very different from the traditional robotics in the manufacturing setting, where the tasks and environments are predefined and fixed. So here, the general-purpose robots require to have several key capabilities. First, the natural language interaction, and it should have strong generalization across different environments, objects, and tasks. And finally, it should be agile, dexterous, and safe. To achieve this goal, more and more recent works have been exploring the foundation models for robotics, benefiting from the significant progress in LMs and VLMs, such as GPT-4, Gemini, Qwen, etc. So these foundation models have strong semantic understanding and impressive generalization capabilities. For example, you can use LM to understand this instruction and then generate codes that interfaces with perception APIs and control APIs to do different tasks. Although these models have achieved very promising zero-shot performance in some robotic tasks, they actually do not fine-tune on any robotic settings. So the accuracy and the reliability remains very limited. Therefore, more recent works have shifted towards the vision language action models, the VLAs. So for VLAs, it fine-tunes the pre-trained VLMs on the internet data further in the real-world robot datasets to directly predict the actions. So as briefly mentioned by Olivier, this is a representative work called OpenVLA. It takes the 2D images and instructions as input to directly predict action sequences. And this model is trained on a large-scale real robot dataset called OpenX embodiment. While this is effective, these models only rely on 2D representations, which can contain several key limitations. First, in the 2D observation space, there are large variabilities due to different camera viewpoints, backgrounds, and lightings, etc. So these models require large-scale real robot datasets for pre-training and fine-tuning to achieve a good generalization capability. And second, these 2D models actually struggle with the spatial understanding and reasoning, as also mentioned in the talk yesterday. So here, even if the state-of-the-art models, the GPT-4, it cannot reliably to predict the metric depths of different objects. To address the limitations of these 2D-based VLMs, our goal here is to propose the 3D VLAs for the robotic manipulation. But it also contains several challenges to build the 3D VLAs. The first challenge is that how should we integrate the 3D information intelligently into the VLAs? What kind of 3D representations we should use? And how to more effectively fuse the different modalities, including the 2D, 3D, language, and robot states. And the second challenge is about the dataset. So currently, compared to the 2D real robot data, the 3D data is actually even more scarce, and it's very hard and expensive to collect these paired 3D observations, language, and action datasets. In this talk, I'll present our recent works to address both this model and dataset challenges. First, I'll introduce our recent work, Point Act, which is a new 3D VLAs with the multi-scale point action interactions. It's a new architecture to integrate 3D into the VLAs. And then I'll present Sugar and Vividex, which are methods that address the data scarcity issues that utilize the synthetic data and internet videos to help train the models. Let's start with the Point Act model. So here we choose the point cloud representations as our 3D representation. So compared to the prior work that many use the depth images, point cloud actually captures more explicit 3D geometries. And compared to other 3D representations like voxels, it is also more efficient to encode. So we study two main approaches to integrate this 3D point cloud information into the VLAs. The first approach is the monolithic 3D VLAs, which inject the point cloud information directly on the VLA backbones. So here, the model will simultaneously deal with all the modalities, the 2D images, robot states, and language, and the 3D point cloud information. So this approach actually has very high computational cost because you can have like hundreds or thousands of points to be encoded into the VLN. And the second disadvantage is that by injecting the 3D information into a pre-trained VLA architecture, it can disrupt the pre-trained 2D VLN representations. Therefore, we also study another approach that is called dual system 3D VLAs. So in this model, we disentangle the semantic reasoning and control by keeping the VLMs frozen and train additional action expert that conditioned on the VLM outputs and the 3D information to predict actions. So in this model, it can address the limitations of the monolithic 3D VLA, but here, only the coarse-grained 3D information are used inside of this model. So the model still remains limited to ground the action predictions in the 3D space. So the key advantage and insights in our proposed Point Act model is that we not only need to preserve the pre-trained VLM semantics with a separate action expert, but we do need to make more fine-grained interactions between the points and actions in this action expert. Here is a detailed architecture of our Point Act model. So here we have a point action expert, which have a fine-grained multi-scale interaction between the points and the actions through this bottlenecked window self-attention mechanism. In this bottleneck window self-attention mechanism, we group points by neighborhood to make it more efficient to deal with thousands and hundreds of points, and we concatenate the actions with each group to make fine-grained interactions. Therefore, the actions can be more grounded in the 3D space. We first perform an evaluation in the simulators. We decided to use two commonly used benchmarks called Libero and RBench. In Libero, it contains 4 task suites, and the action space is the delta end effect pose using micro steps. And in RBench, it contains 10 tabletop manipulation tasks and use the key actions, which represents 2 longer horizon actions. And the RBench task is actually more challenging than the Libero one because it contains larger spatial variations and more challenging tasks. So let's first see the results on the Libero benchmark. On Libero, we achieve very strong performance with only a single front view RGBD camera and without any pre-training on large-scale robot dataset. So we compare both the previous 2D VLAs and the 3D VLAs. Compare the 2D VLAs like Pi0 and Groot from NVIDIA. We actually do not require any pre-training and outperform them. And compared to the 3D VLAs, the spatial VLA, which only utilize the depth information, we found the point cloud information is more beneficial for the VLA to understand the geometry. And then for the RBench benchmark, we have achieved more significant improvement on this. We obtain like more than 10% absolute improvement, because this benchmark actually requires more generalization to different placements of objects, require stronger spatial generalization. And with our 3D information, it benefits more. We further deploy our model on the real robot setups. We include 2 robots. One is the SO100, which is a cheaper one from Hugging Face, and the UR5 robot platforms. On these 2 different approaches, we use different action spaces due to the convenience to collect demonstration data. So here we show the demo of the model. Okay. So in UR5, we perform 3 different tasks. Here is put fruits on plates, close drawer, and stack cups. And in SO100, we also perform 3 tasks, and it can execute very well. Quantitatively, we achieve comparable and slightly outperforms the previous Pi0 model that pre-trained on large-scale real robot dataset. But here, as Oliver mentioned, that the speed is also an issue. So here you can see that we accelerate the video by 4 times. And I'll talk about the speed in the last part of my talk as a future work. Yeah. And here are more ablation studies of our model. So for fair comparison, we compare models that only trained on downstream tasks without the real robot pre-training. So first part is the monolithic VLA. We use the EO1, which is based on the Quen VLM backbone. And we can see that although the 3D point cloud information helps on the liberal benchmark, which is the easier one, but it actually decreased the performance a lot on the RBench, which is a more challenging benchmark. So this is because adding the point cloud information into the VLM backbone can destroy the original representation and make the training very unstable. This is why it performs very poorly on the RBench tasks. And but for the dual system VLAs, it becomes more stable when adding the 3D point cloud information. So we can see that in the GROOT, we use the architecture without pre-trained checkpoints. Adding the 3D information always helps on different benchmarks. And our proposed point act with dense interactions of points and actions really ground the action prediction in the 3D space and achieves the best performance. And then we show the model size scaling and the importance of pre-training these point cloud encoders. So here, from left to side, we compare different sizes of the point cloud encoders from small, base, and large. We can see that without the pre-training of the point cloud encoder, the performance can be unstable with increased model parameters. But if we have some pre-training, the performance can be continuously improved. Here, the pre-training of the point cloud is not done on the large-scale real robot data, but it uses the static building level sims to do a self-supervised pre-training to just learn the point cloud encoder. So there is still a large domain gap compared to these building level sims and our tabletop scenarios. So a summary of this work is that the current dominant 2D VLAs lacks the spatial reasoning for robust robotic manipulation, and it's important to integrate 3D into the VLAs. And our proposed point act model provides a multi-scale point interaction method to more effectively improve the 3D VLAs. And our clear future direction is that to pre-train these 3D VLAs on domain-specific, manipulation-specific datasets to further improve its generalization capability. And this is what we are going to discuss in the next part, how to pre-train these 3D point cloud encoders to make it more generalizable. So in this work, Sugar, we propose to use the synthetic data to learn the point cloud encoders. So here, I first want to discuss what kind of properties we want to capture in these point cloud encoders. So first property is the geometry understanding abilities. For example, from a partial view of the object, we want the point cloud encoder to be able to infer the unseen areas, unseen shapes of the object to have these geometry priors. And second, we do not only want to deal with a single object manipulation, we want to do the manipulation in a cluster sense with multiple objects. So it's important that the point cloud encoder can deal with the multi-object scenarios. And then because we want to have the natural language interactions, so it's important to ground the natural language aligned with the point cloud representation. And last but not least is to really learn the affordance of the objects from this point cloud representation so that we can infer what kind of grasping poses we should apply on the objects. So merge all these different properties, we propose this sugar representation. And then the key question is, how do we train these 3D representations, and what kind of data sets we should use to train these point cloud encoders? On the internet, we have seen a large scale of single 3D object assets. For example, the Objectverse, ShapeNet, and furniture data sets, which contains like about over 1 million of single objects. But the problem is that this data set only contains the 3D meshes, but without any labels. So we follow a prior work called OpenShape to use 2D VRMs to generate text descriptions for images of these 3D assets, and then use LLMs to further merge these multi-view descriptions as a more coherent and accurate description for 3D objects. Therefore, we can obtain the payload data of the single objects and their semantic labels. But as I said, besides the single object manipulation, we care more about multi-object manipulations. So we further build multi-object datasets. Here we use a very simple strategy to build the multi-object themes. So we first select some support planes, for example, a sofa or a table, and then we randomly put small objects on top of these support planes. Then, in this way, we create diverse themes, and then we need to generate labels to train our model. Similar to the single object pre-training, we can use the VRMs to generate the text descriptions. Because these assets can be imported into a simulator, so we can obtain the ground truth, depth, and segmentation masks from the simulator. And also benefiting from the physical simulators, we can automatically generate the grasping poses for each object. And using this way, we can automatically generate large-scale single object and multi-object datasets together with the ground truth labels. And then we train our point cloud encoder on this large-scale synthetic data. We propose a curricular learning approach to train on these datasets. We first start with the single object pre-training. We use the master point modeling that masks the objects, part of the object, and predicts the master areas to learn the geometry properties. And then we use a similar way as CLEAP to do this cross-model learning to align the point cloud representation with the semantic labels. After pre-training on these single object datasets, we further extended it to do a joint training with the multi-object scenarios. So here we propose the grasping pose generation tasks, the instance segmentation tasks, and the referring expression grounding tasks to jointly train the whole model. And after the pre-training, we use the point cloud encoders as a representation for the downstream manipulation tasks. Similarly, we use the R bench as simulated environments to evaluate our pre-trained point cloud encoders. First, let's see the impact of this pre-training. So on the leftmost part, we have the performance of the model without any pre-training, just train on the downstream task. And then we add single object pre-training, and after this, we can see a slightly improvement. And the larger gain can be observed from this multi-object pre-training because this is more aligned with the downstream tasks. And we further explore the few-shot evaluations. When you have a small downstream task data sets, then the benefits from the pre-training become significantly larger. So a summary of this work is that we propose to use the simulation to generate synthetic data to learn the 3D representations. And we further propose this curricular learning approach to make the 3D representation learning more effective. And there are quite some future directions to improve, especially on the synthetic data generation part. So in the multi-object datasets generation, we only use a very simple strategy to generate these multi-object scenes, which might not be so realistic. So a next direction would be to use LMs and diffusion models to generate more realistic environments. And this is our recent work that used the LM to generate a layout of the scene and then use the diffusion models to generate each single object and place them according to the layout from the LMs to build a more realistic environment. And this approach can be further used in the 3D space to generate more realistic scenes for the model training. Okay, then I come to the last part, because the sugar method only pre-trained on the static 3D environments. It can only learn this, improve the perception, but if you want to predict actions, you still need some dynamic robot interaction data to train the model to predict action. And for this, it's still very data consuming. There are two ways. One is just to use teleoperation to collect more demonstrations and use that to train the model, which is very hard to scale up. And another approach is to simply use the reinforcement learning to train the policies, let the model to explore in the environments. But this requires a handcrafted reward design to be scalable, and it's very computationally expensive. Therefore, in this work, we propose another approach to learn from the human videos, because the human videos are very abundant on the internet, and there are large similarities between the human manipulation skills and the robot manipulation skills, especially for the five-finger robot hands. Then how can we learn from these human videos? Given a human video, we can first do the automatic 3D reconstruction to generate the human hands, to reconstruct the human hands and the interactive objects. And then, because we know the alignment of the human hands and the robot hands, we can do a motion retargeting to convert the human hand motions into the robot hand motions. This can be achieved by a trajectory optimization method. But this generated trajectories, we call it a reference trajectory. But this reference trajectory has several limitations. First, because of the imperfect 3D reconstruction, the reference trajectory is very noisy. And also, the videos only contains a partial information. It doesn't contain all the physical properties of the manipulation side. So because of this noisy reference trajectory, we cannot directly rely on this kind of data to train a good policy. Then how can we learn from this noise reference trajectory? We propose a two-stage method. In the first stage, we learn a state-based policy in the simulator for each video. This state-based policy can convert the noise trajectories into a more physical plausible trajectories that can further used into the second stage as imitation learning data. And then in the second stage, we train a unified visual policy that can take all the previous data sets and then to predict actions directly based on the visual signal without knowing any the privileged state-based information. So the key here is how can we improve this state-based policy learning from these noisy action trajectories. To do this, we propose a trajectory-guided reinforcement learning algorithm. This aims to improve the reward functions with the reconstructed 3D human motions. So we divided the manipulation phase into two parts. In the first stage, it's called pre-grasp stage. So here, we mimic the human motions to approach the object. So here, the reward signal is the similarity of each human joints and the robot joints. And the second stage is called manipulation phase. So in this phase, the object is manipulated by the robot hands. So here we define the reward function to mimic both the human motions and constrain the target object to have the similar object motions as shown in the video. So we combine these two different rewards of both hand and objects together with the sparse reward of the final target as the final reward function. And we use this reward function to train in the simulator with the PPO algorithm. And since this reward function is purely derived from the human videos and the reference trajectories, this can be applied to many different manipulation tasks. So in the experiments, we first conduct the simulation experiments on 3 manipulation tasks called relocation, which is to grasp an object and place it into a target place. The purring aims to pour some particles from a cup to another place and placing inside to pick up one object and place in another container. And for the videos, here for simplification, we use the DEX YCB dataset, which contains like fixed view captured in lab conditions. So you can clearly see the objects and the human motions. And we compare our model with a state-of-the-art method called DEXMV. In DEXMV, it actually directly uses these noise trajectories as an imitation learning objective together with the reinforcement learning to train the policy. So it requires to use the large-scale videos in order to learn a good policy because these trajectories from the videos are quite noisy. But compared to this model, we only use one single video and can achieve much better performance than the DEXMV method. And the datasets generated from our state-based policy can be distilled to another vision-based policies and achieve comparable performance as the state-based policy. And then we also perform several ablations to examine the impact of the proposed 2-stage reward. We can see that the rewards from both stages, the pre-grasp and manipulation, are both important for the final success. And we further show some scaling laws of expanding our methods to generate more data sets. Here we use more videos to generate the trajectories and use that to further train our vision-based policy. And you can see that with more videos, the performance can continue to improve. Finally, we deploy this method on the real robots with the Allegro-Han and the UR5 arms. And here I show some demos that our model can be deployed to relocate different objects. These objects are seen in training. And it can generalize to diverse objects, diverse poses of these seen objects, as well as generalize to some unseen objects. Yeah. So a key takeaway from this ViviDex work is that we can learn from the human videos, but we shouldn't take the noise trajectories from these human videos directly as an imitation learning objective. We should use it as, for example, use it in a reward function and use that to accelerate the reinforcement learning. And this also provides a scalable method that can be applied to different videos and collect more realistic robot demonstrations automatically from the abundant human videos in the wild. And one limitation of this work is that we only use the lab-captured videos where you can perform the 3D reconstruction more accurately. And the next direction would be to deploy this to in-the-wild videos. Then the 3D reconstruction is more challenging. So we further deploy and propose new methods to improve the 3D object and hand reconstructions for in-the-wild videos. So this work, called HOT, which was accepted by ICV last year, is to use the large-scale synthetic data to pre-train the transformer model to generate high-quality object reconstructions. So to conclude, in this talk, I presented our VLA model, point act model, which integrates the 3D point cloud information into the VLAs to make it more generalizable. And then to address the 3D dataset scarcity problem, we use the synthetic datasets and learn from human videos to get more robot training data. And what is next? So here are some directions we are currently also doing in our team. The first part is that for VLAs, only use the vision information is certainly not enough. So we are also exploring to use touch and force enhanced sensors to improve the robustness and scalability of VLAs. And second part is about word modeling and planning. We are exploring to build hierarchical, stochastic, and 3D-based word models to further enable the model to perform long horizon planning and ensure the robustness of the actions. And last part is about reinforcement learning. Because currently we mainly generate the supervisor data to train these VLAs. Then, especially for the speed problem, we cannot really have a very fast method that can improve the demonstration speed. So I think here the reinforcement learning can be a very good method to further improve the speed and robustness of our policies in the real world. And my goal here would be to have a general purpose policy that can both achieve good generalization and agility in the future. And that's all. Thank you for listening. Yeah, I'm happy to take any questions.
Nicolas?
Excuse me. Yeah, thank you. I'm interested in the point cloud approach. So what's the granularity on the point cloud? And how do you actually train that model?
OK. So for the point cloud, we actually first crop the workspace according to the robot base. Like it would be like 2 meter times 2 meter squares. And then we work slice the point cloud using the 1 centimeter squares. Yeah. And this would be the resolution of the point cloud. Definitely it's not like fine-grained enough, but in the future we plan to integrate this point cloud, sparse point cloud information with some like more fine-grained 2D information so that you can have more granularity for the point representations. And in terms of training, currently we only do the imitation learning. So we have the real robot, we have the robot demonstrations, and we use this kind of data to train the model.
I thought you were actually also training the point cloud representation with something like a VLA or something, but I missed that part.
Yeah, so it is end-to-end training. Because the model is like an end-to-end pipeline, so we use this like imitation loss and backpropagate to both the VLM backbone and also this point cloud encoder. But the VLM is, the backbone VLM is frozen because we do not want to ruin the features. Yeah.
Thank you very much. Maybe a stupid question, but for the next step, and because I understand that you have a lot of videos that you can train from, but for the robot manipulation, you would need, as you said in your perspective, touch and to have the grass, I would say. And how do you foresee to get info to train the models for that?
Yeah, the human videos, although they are abundant on the internet, they are actually untrained. So definitely there are a lot of pre-processing steps are needed to get high-quality robot data. First, I think it's necessary to use the current like video VLMs to get more segmented videos, for example, only for some automatic action skills. And then we could do 3D reconstruction to reconstruct the hand and the object motions from the video and build a synthetic environment that we can learn the action skills in the simulator to reproduce the actions. And in this way, we can obtain like high-quality robot demonstrations for the downstream VLA training.
No, just for the force that you will need to also learn how to apply the force for certain tasks where maybe if you want to squeeze, you have a bottle, you want to put some ketchup, I don't know. So the video, I don't know if it's what would you will use as a ground truth to know what are the forces you need to put on the
Yeah, this is a good question. Because we cannot obtain this force information from the videos, this is why we convert the 3D meshes into a simulator. And in simulator, we can predefine these forces and what can any other like physical properties, and then use reinforcement learning to train. Yeah.
And just a small comment. So actually with Shizhe, we will be actually collaborators in the PPR acceleration. There will be the core AI, where we will have a PhD with Ruffin and collaborating with Shizhe to do data sets. And collecting in our lab, we have a humanoid robot with tactile sensing to collect data and to go into nice simulators.
So you told us quite a bit also about vision and action. Didn't hear much about the language component. So what are you doing about that?
Yeah, so currently we mainly borrow the knowledge from the the VLM backbones and inject language inside. I think the main benefits from the language is to do some high-level planning, because with videos you can generate a short-term video to recover the physics or predict the object state changes, but it's hard to perform a very long-term planning. But with language, we can abstract this information and to do some sub-task generation and use these sub-goals to guide the policy learning. So this is the advantage of this language. And I haven't mentioned in our point act paper, because currently we haven't used this language to do this sub-task planning, but this would be our future work.
But also, I mean, language could be very useful in the description component of the task, right? But there, then I'm a little bit more skeptical that just the point cloud geometry will suffice, because in language we need to talk about relational aspects between objects, and those relational aspects are often underspecified. And since you're assuming a kind of complete and precise geometry, that runs into a problem. And we know about this from linguistics for, I don't know, a lot of years, that one way to do this is to supervaluate and to look over all possible completions of the information, but that's super inefficient. And you won't be able to compute that very well. So I think it's worth thinking about actually the linguistic aspect, not only for planning, but also for description, and also for teaching. Because you're just using, you're using vision, but when we teach, we use conversation and we use vision combined. And that's kind of what we're trying to do in the chair with Olivier and Ruffin.
Thank you for the comments. And this also will be our ongoing work. So as I mentioned in the reinforcement part, I think it's good to provide a good reward function to help the policy learning, right? Then the human feedbacks through the language would be a very effective tool to guide this learning.
That's what we think too.
Yeah.
One last quick question.
Thank you very much. It was exciting. My question is about the qualification of the quality of the videos you feed in your system. If you show a video of an inexperienced worker that does not manage the job correctly, of course it will not be a good example for teaching. So I know there are plenty of companies that are losing experience from old workers. They are going to retire. They are very interested in capitalizing knowledge, and I imagine how useful it could be. So do you think to choose samples of highly experienced workers? What is your approach here?
Yeah, thank you for this question. So there are some other works in our team from Houston. Yeah, so he has done quite some works on reinforcement, especially for offline reinforcement. For example, they could provide some good metrics to select high-quality data sets to enable the model to learn better. And also, I think besides this offline reinforcement, online reinforcement is also important to improve upon these experts, right? You want to have superhuman skills, not just mimic the humans. Yeah. Thank you.
Thank you very much.